My talk, the foundation of C++ atomics, the knowledge you need to correctly use C++ atomics, is a series of talks about atomics. And today I will present the first in this series of talks. Here we have the anatomy of C++ atomics. This is how I see C++ atomics. Just put my timer. This is how I see C++ atomics. I divide them in 4 key components that one needs to know in order to understand atomics. Need to understand atomics as a class in C++. For example, how atomics interacts with the other parts with other features of the language. Need to understand the guarantees that are given by the C++ memory model. Need to understand how atomics interacts with compiler optimizations, and need to understand how atomics interacts with hardware optimizations. Today, I will focus on hardware. The first talk in this series of talks will be about hardware. I would also like to acknowledge the work of Onur Mutlu. He's a professor at ETH Zurich. And I used to watch a lot of his lectures on computer architecture. And some of the slides present in my presentation today were inspired and others directly taken from the slides of his lectures on computer architecture. As I said, the first talk will be about hardware, so that's why it is important to start with a brief description of a computing system. A computing system has 3 key components: computation, communication, and storage and memory. And these 3 key components are used to create different platforms that have to achieve different goals or metrics, as you can see in these pictures, in the slides. There is no need for atomic operations if there is no need for atomic operation if there is no parallel computers. So that's why it's also important to understand why parallel computers. The original goal was to improve performance, and there is also other goals like to reduce power consumption, to improve cost efficiency and scalability, and to reduce complexity. And there is also the goal to improve dependability. I'm going a little bit faster because all of this information is just to give the background and context to understand the rest of the talk. And there is 2 types of multiprocessors. There is loosely coupled multiprocessor, and there is tightly coupled multiprocessors. And for the rest of the talk, I will only cover tightly coupled multiprocessor, where we have a network of cores that are sharing a global memory address space. And the C++ standard does not support programming for loosely coupled multiprocessors. There is a lot of issues with tightly coupled multiprocessor, but today I will mainly focus on memory consistency. So here we have a processor-centric design. And in this processor-centric design, we have a network of cores that are connected by a shared interconnect. And these cores are sharing memory. So the question is, why do we need atomics? And the answer is, we need atomic operation for 2 reasons. First is atomicity. With atomicity, we want to ensure that only one core at the time is operating on a particular memory location, and the rest of the cores cannot see this operation partially done. We also need atomic operation for synchronization or visibility. And with that, we want to ensure that the result of the computation of cores can be visible to other cores when needed. That's why we need atomic operations. So now let's understand the difference between memory consistency and cache coherence, because it will also be important for the rest of the talk. Consistency is about ordering of all memory operations from different processors, that is, to different memory locations. It's a global ordering of access to all memory locations. And coherence is about ordering of operation from different processors to the same memory location, a local ordering of access to each cache block. So with consistency, we care about operation, we care about the order of operation on our memory locations. But with coherence, we only care about the order of operation on a particular singular memory location. So that's the difference between coherence and consistency. Now let's talk about memory ordering in a MIMI processor. It's a multiple instruction and multiple data processor. Here, each processor memory operation are in sequential order with respect to the thread running on that processor. And we assume that each processor obeys the Van Neumann model. And what I mean by Van Neumann model here is that the architecture state are updated in the program order specified by the programmer, right? So the microarchitecture can perform optimizations that preserve the semantics of a single thread and also update the architecture state in the program order specified by the program. And also here, multiple processors can execute memory operations concurrently. So the question is, how does the memory see the order of operation from our processors? In other words, what is the ordering of operations across different processors? So let's understand why this question is important. Let's understand why this question is important using this example. Can the two processors be in the critical section at the same time, given that they both obey the Van Neumann model? The answer is yes. And the other question is, what does the second question? What the second question has to do with the first question? What the second question has to do with the first question is that these two threads can be at the critical section at the same time because the threads don't agree in the order in which the memory operations took place. Now let's understand how this example works. So here we have two threads, and both of the threads have global variables that are used as a flags to communicate to other threads when the thread is in the critical section or not. And here we also have some letters A, B, C, and D that I just use them to indicate instructions. So when I say instruction A, I mean the global variable S1 being set to 1. Now let's understand how this example works. So when a thread wants to enter the critical section, first the thread set his flag to 1, and in this way the thread is communicating to other threads that he is in the critical section. And after that, the thread checks the flags of the other thread to see if the other thread, in this case the thread number 2, is in the critical section. And if the flag is equal to 0, it means that the second thread is not in the critical section, so this thread can enter the critical section. But if the flag of the other thread is 1, this thread cannot enter the critical section. And the same behavior applies to the second thread. So before we go into details why and how these threads can be at the critical section at the same time, let's understand why it's important to protect shared data. Threads are not allowed to update shared data concurrently for correctness purposes, and access to shared data are encapsulated inside critical section or protected via synchronization constructs like locks, semaphores, and condition variables. And only one thread can execute a critical section at a given time. This is the mutual exclusion principle. And a multiprocessor should provide the correct execution of synchronization primitives to enable the programmer to protect shared data. So here I just illustrate why it is important to protect shared data. Now let's go into detail and in a sequential manner how and why these threads can be at the critical section at the same time. So here I have the two threads, and here I have time that just describe the time in which event happens. So let's start. At time 1, the thread 1 set his global variable to 1, but the thread 1 is not updating the memory directly. Instead, the thread 1 is writing to a local buffer. But for the point of view of the thread 1, this operation is complete, even though the thread will update the memory later. And the thread 2 do the same with respect of the of his flag, the thread the flag S2, like the variable S2. Instead of updating the memory directly, also updates to a local buffer and will update the memory later. So at time 2, the thread 1 checks if the flag of the thread number 2 is equal. Okay, at time 2, the thread 1 checks if the thread number 2 is in the critical section, right? But while loading the flag of the thread number 2, it's a cache miss, so need to send a request to memory. And so the thread start loading the global variable of the thread number 2. And the thread number 2 does the same here with respect of the flag of the thread number 1. So at time 3, the request that the thread number 1 sent to memory arrives, and the thread 1, okay, and the thread 2 and the thread 1 sees that the flag of the thread number 2 is 0. Why? It's 0 because this value still didn't propagate to memory, right? The value that was writing to the flag by the to the variable S2 by the second thread still didn't propagate to memory, still on the local buffer. So that's why the thread number 1 here is seeing 0. And the same thing happens with the thread number 2 with respect of the flag of the thread number 1. And because of that, at time 4, both of threads enter the critical section. And we saw in the previous slides that 2 threads cannot be at the critical section at the same time, because if 2 threads are in the critical section at the same time, there is the probability that these 2 threads will be operating at the same memory location at the same time. And this is a problem. So at time 5, the instruction A completes. The thread 1 updates the global S1 directly to memory, sent to memory. And the instruction C also completes, and the variable S2 is in memory, but it's too late because the 2 threads are already in the critical section at the same time. So what's the problem here? The problem is that threads don't agree in the order in which memory operations took place. For the thread 1 point of view, the instruction A happens before instruction C, but for the point of view of thread number 2, the instruction C happens before A. So there is no consensus here. And both of threads cannot be correct. The problem, 2 processors did not see the same order of operations to memory, and the happens before relationship between multiple updates to memory was inconsistent between 2 processor point of views. As a result, each processor thought the order was not in the critical section. So how can we solve this problem, right? How can we solve the problem? An idea is to use sequential consistency. And here I have a formal definition of sequential consistency, but I will use a more abstracted way to explain sequential consistency. So in sequential consistency, memory works as a switch. And when the switch points to a thread or processor, we have the guarantees that all the memory operations performed in that thread or processor will be visible to other threads or processors in the system. In that way, we can create a total order in which all the processor or thread agrees in how memory operations took place. And here I have an example of sequential consistency execution graphs. As I said, it is a series of talk about atomics, and the focus of today is hardware, so there is not really enough time to go through this example. But I would like to mention here is that even when we are using sequential consistent memory model, the execution of a program can still have multiple orders of execution, right? A program even though it's using sequential consistency, can still have different orders of execution. And which order is observed depends on implementation and dynamic latencies. So now let's talk about issues with sequential consistency. Sequential consistency is a nice abstraction for programming, but have two issues: too conservative ordering requirements, and limits the aggressiveness of performance enhancement techniques. And we have a question: is the total global order requirement too strong? Why? Because the ordering of operation is important when the order affects operation shared data. That is, when processors need to synchronize to execute a program region. Let's use an example here. So in a single thread, we can have local variables that we are not sharing with other threads or processors, right? For example, we have an array of 100 positions, and we are operating on this array. Do we need to make this array, the operations that are done in this array, visible to other threads or processors in the system? Well, we don't need, because we are not sharing this array. This array is local to a thread. But in sequential consistency, we need to these threads, but in sequential consistency, the operation on this local array need to be visible to other threads, even though no one needs to see it. So it raises the question, how about a global ordering only across our stores, like the total store memory model, for example, that I used in x86 architecture? Or how about enforcing a global order only at the boundary of synchronization, like acquire and release consistent model, for example? So, for example, when we are using locks, right? When we are using locks, we only need to ensure that the operations inside the critical section do not exit the critical section. But memory operations outside the critical section and inside the critical section, they don't need to be executed in a sequential consistent manner. And also because sequential consistency affects performance, computer scientists and engineers have proposed techniques to speed up sequential consistency memory model. So here we have a proposal at the hardware level. And here we also have a proposal at the compiler level to speed up sequential consistency. And also, because sequential consistency affects performance, there is also proposals for weak consistency memory model, like the acquire and release memory model. Again, I will not go through the memory models today because we have a special talk that will be cover this, and also because the focus of the talk today is the hardware, right? So how techniques used by computer architects can affect the memory model of an architecture. So the C++ programming language also offers support, or also provides support for memory ordering, acquire, and release, as we can see here. Again, I will not go through this. And the C++ programming language also offers even a more relaxed memory model, that is the relaxed memory model. And if you want to understand these execution graphs, mathematizing the C++ concurrency is the paper to read. So we saw in the previous slide that two threads can be at the critical section at the same time, because the threads, instead of updating the memory directly, these threads were updating a local buffer. This outcome may be surprising to some of us, but this outcome is actually expected from almost all modern computer architectures today. So some architectures, so the memory model of some architectures are affected by the buffer and also other mechanisms that are used at the microarchitecture level. But the TCO memory model, the memory model also used by the x86 architecture, is only affected by this buffer. So the rest of this talk, I will be covering how the real buffer, also this buffer is also called the real buffer or store queue, affects or influences the x86 total store memory model. So the goal of the talk is to understand how the real buffer within x86 cores influenced the x86 total store memory model. So let's start by making by comparing the TCO memory model with sequential consistency, because we also cover sequential consistency, and the TCO memory model is close to sequential consistency memory model, but there is a difference, and we are going to see this difference now. The difference now. So sequential consistent execution are a proper subset of total store execution, and all sequential consistent execution are total store execution, while some total store execution are sequential consistent execution and some are not. With that, we can conclude that total store memory model is weaker than sequential consistent memory model. Why? Again, because all sequential consistent execution are TCO execution, while some TCO execution are not sequential consistent execution. So here we have another example that will help illustrate the difference. So for both sequential consistency and TCO, loads and loads cannot be reordered, loads and stores cannot be reordered, and stores and stores cannot be reordered. But in TCO, a store can be reordered with a subsequent load. But under sequential consistency, it cannot be reordered. So that's the difference between total store memory model and sequential consistency memory model, right? In total store, a store can be reordered with a subsequent in the program order load. So systems that support TCO do not provide ordering between a store and a subsequent in program order load, although they do require the load to get the immediate value of the early store. In situations in which the programmer wants those instructions to be ordered, the programmer must explicitly specify that ordering by putting a fence instruction between the store and the subsequent load. Again, for the rest of the talk, we cover hardware. We start to understand how the real buffer within x86 cores influenced the x86 total store memory model. So before we start talking about hardware, so why is it important to understand the hardware when we are studying or trying to understand memory models? First, it's the knowledge that one needs to verify if the compiler is providing an efficient compilation to hardware. And I have some questions here to help illustrate that. Do we need fences to implement sequential consistent memory model on x86 architecture? The answer is yes, but why? Do we need fences to implement the acquire and release memory model on x86? The answer is not, but why? Why the compiler and hardware change the order of execution of instructions? The answer is performance. But why it's possible to gain performance by reordering instructions? Right? If one wants to really understand this question that are very much related to atomic operations, it's important to understand the hardware. Especially if you care about performance and you want to verify if a compiler is really providing efficient compilation, it's important to understand the hardware. So the other question is why to keep a buffer inside of a core? So why this question is important? Well, this question is important because almost all modern architectures use a separate buffer. So this buffer has influenced the memory model of almost all modern computer architecture that we have today. So that's why it's really important to understand this buffer. And as I said, this talk, this series of talk is called the foundation of C++ atomics, and understanding hardware is really part of the foundation. So the answer for the question, why to keep a buffer inside of a core, the answer for this question is different for architecture to architectures, but some architectures use the write buffer to provide precise exception and to help solve the problem of memory disambiguation. And going forward, we will see why. You don't need to understand all of this right now. Going forward, it will be clear. And the other reason that we have this buffer inside of the architecture is to support, right, high performance execution of programs. And we will see also why going forward, why and how going forward. So for the rest of the talk, it's important to understand data dependencies. And we have three types of data dependencies. There is flow dependencies, that's a read after a write. Here, the first instruction is writing to register number 3, and the second instruction is reading register number 3. So we have a true dependencies over here because the second instruction cannot execute until the first instruction completes, right? Because he needs the value that will be writing by the instruction number 1. And there is also anti-dependency, that's a write after a read. And here, the first instruction is reading register number 1, and the second instruction is writing to register number 1. We don't have true dependency over here. The problem that we have here is that we don't have enough registers in our architecture. And if there is enough registers in our architecture, we can replace the register number 1 at instruction 1 with register number 15, and the semantics of the program will still be preserved. There is also output dependency, that's a write after a write. Here, the first instruction is writing to register number 3, and the second instruction is reading register number 3, and the third instruction is writing also to register number 3, right? Even though we have a true dependency between instruction 1 and instruction 2, there is no true dependency between instruction 3 and instruction 1. The problem that we have here is also because we don't have enough registers in our architecture, because if there is enough registers, we can replace the register number 3 at instruction number 3 with register 20, with register number 20, and the semantics of the program will still be preserved. So that's not good for high performance processor, because all these dependency will affect the performance of the processor. So in order to eliminate, there is a lot of techniques that are used there is techniques that are used to eliminate the anti and output dependencies. For example, that are used to eliminate this dependency. We use computer architects use buffers to perform renaming, and the flow dependencies cannot be eliminated. It can only be tolerated, and it's tolerated by giving restricted data flow machines. So we don't have enough time to cover all of this, but you can watch my CPPCon talk that will be available at the YouTube channel of the CPPCon, where I will go into detail how these dependencies are eliminated and how modern machines tolerate flow dependencies. But it's important to understand the out of order. It's important to understand out of order execution, also dynamic scheduling, because it is crucial, right, to understand atomic operations. So that's what for now we are going to understand that. Also, this is an example where I just illustrate how all of this works. Again, we don't have time to go through this. I describe all of this in my CPPCon talk, but we really doesn't have enough time to cover all of this. So I will just give an abstracted explanation of an out-of-order execution. So in an out-of-order execution, we fetch here we have an illustration of a pipeline. So we fetch an instruction. After fetching the instruction, what we do, we allocate an entry of that instruction into the reader buffer. It's the write buffer, the buffer that we are talking until now. So now we are going to see one of the use of this buffer at the microarchitecture level. So at the code stage, we allocate an entry for that instruction into the reader buffer, and we do that to provide precise exception, right? We don't want to update the program. We don't want to update the state of the program out of order. In order to update in the program order and to provide precise exceptions, we allocate an entry to that buffer, so that this buffer will update the architecture state in the program order specified by the program. So, and also after that, after we allocate an entry into the reader buffer, what we do, we perform register renaming, and we perform register renaming, or just renaming, because we do that for registers and also for memory operations. And we do that to eliminate, right? We do that to eliminate anti and output dependencies, right? Renaming is the technique that is used to eliminate anti and output dependencies. So that's where we perform renaming. So after we rename an instruction, what we do, we move the instruction to reservation stations. And the reservation station is the technique that we use, again, sorry for that, to tolerate flow dependencies, right? The reservation station is the technique that we use to tolerate flow dependencies, because we are now making all the instructions wait into a special place, that wait for the operand in a special place called reservation station. So here we also have multiple execution units. So at the reservation station, when the instruction will go after the operands, and when the operands of the instructions are ready, we can move the instruction into a functional unit, right? And we have multiple functional units. We have integer addition, we have integer multiplication, floating point multiplication, and so on. But it's important to understand that these function units have different latencies, right? For example, the integer addition takes 1 cycle to complete one instruction, and the integer multiplication takes 4 cycles to complete an instruction. And because of that, this instruction can update the architecture state out of order. And it's also important to mention that here, the only requirement to execute an instruction is that both of the operands, or all the operands of the instruction, need to be ready. When all the operands of an instruction is ready, we can dispatch the instruction to a functional unit, right? We are completely executing instruction out of order, right? We don't care about the program order. We don't care what the programmer have specified The only thing here is that we will, right, respect the dependency, the flow dependencies, the true dependency will be respected, but we will execute instruction out of order. We will not follow the program order. And the only requirement in this machine is that all operands of the instruction need to be ready to be executed. And as we see, and when the instruction completes, it's out of order, but the instructions complete out of order, but don't update the architecture state out of order. They update the reorder buffer out of order, and the reorder buffer updates the architecture state in the program order specified by the program. So we have an in-order dispatch, an out-of-order execution, and an in-order update of the architecture state. So here is an example of how modern machines perform register renaming and provide precise exception. So it's an example of the Pentium 4. We have this front-end register alias table that, together with the reorder buffer, I use it to perform register renaming to eliminate anti and output dependencies. And the retirement register alias table with the reorder buffer, I use it to provide precise exception. In other words, to update the architecture state in the program order specified by the programmer. So now let's understand a little more about out of order dispatch. So the benefit of an out of order execution is that we can tolerate latencies. It allows independent instruction to execute and complete in the presence of long latency operations. Here we have an example that we help illustrate the difference of the, I would say, the normal way, right? We see, we think computers execute instruction, right? The first instruction that is the computation of x plus y, and the second is the division of y plus y divided 10. Is the division of y by 10, and then the third instruction is the a times b. So, and when normal we as a program we see a program like that, we think that the processor will execute the first instruction and then the second and then the third instruction. Well, but modern computers, modern high performance computers, processors are restricted data flow machines. And now we are going to understand here what is a data flow machine. In a data flow machine, the only requirement here, the requirement to execute the second instruction is that the first instruction needs to complete. But here in a data flow, the requirement to execute, right, an instruction is that the operands of the instruction need to be ready. As soon as the operands of the instructions are ready, we can execute an instruction. Now let's see. So the first we transform, right, these instructions into nodes. For example, here we have the node addition that depends on two operands, that is the x and y. And the node addition to be executed, we need the x and y to be ready. And we have the node division that depends on y and a contrast 10 in order to execute. So let's see how this instruction can be can execute out of order. So when the y operand is ready, because the another operand of the division node is 10 and it is fast to get because 10 is a constant, well, this division we can execute. But the addition cannot. Why? Well, because both of the operands are memory, and to access memory takes time. So that's why even though y is ready, x is not ready, but both operands of the addition are ready, so we execute the addition. But it contradicts the program order that we see here, because now the second instruction is being executed while the first instruction didn't complete. So this is here we have an example for data flow machine. So the time doesn't allow to go through all of these. I would suggest you to write my CPP con because we really need to go to the most important. And here is my mental model of an out of order or a data flow machine. Here, instruction fires when the operands are ready, right? We preserve data flow semantics, right? We eliminate anti and output dependency by performing renaming, and we fire when the operands of the instructions are read. So that's my mental model of a data flow processor. So that's good because now we eliminate anti and output dependencies, and we also can provide precise exceptions. And also we can tolerate memory latencies of data flow dependencies. So now let's talk about handling out of order execution of loads and stores and how this affects the total store memory model. So first, let's understand the difference between registers and memory, because it's really important for the rest of the talk. So the first difference between registers and memory is that register dependencies are known statically, and memory dependencies are determined dynamically. Register state is small, and memory state is large. Register state is not visible to other thread or processor, but memory state is shared between threads or processor in a shared memory multiprocessor. So here we really have the goal of the talk, right? We will see how the way modern processor handles execute of load of stores affects the visibility of stores operation, and also why in ECT6, for example, we don't need fences for stores and store operation, between stores and stores. So we need to obey memory dependencies in an out-of-order machine or a restricted data flow machine, and we need to do so while providing high performance. So the observation and the problem: memory address is not known until a load or a store executes. Let's understand this a little bit. So when the operands of an instructions are only registers, we know, right, which register we need to access, right? We know the IDs of the registers at decode stage. It's statical. We don't need to compute anything to get the IDs of registers. And the only thing we need to check the dependencies between instructions that only use register is just the ID of register. But memory operations are different, right? For memory operation, first, we need to compute the address. We cannot dispatch a load or a store before we compute the address. So that's one of the difference. So let's understand the problems that we have with memory operations. First, renaming memory address is difficult, and we will see why. Second, determining the dependency or independence of a load or store has to be handled after the partial execution, as I just stated, that we cannot dispatch loads on store before computing the address. And the corollary number 3 is that when a load or store has its address ready, there may be older or younger stores or loads with unknown address in the machine. And this third corollary is also called the memory disambiguation problem. And here we are going to understand this problem. So the first question is when to schedule a load instruction in an out-of-order engine. The problem is that a younger load can have its address ready before an older store's address is known. It's also known as the memory disambiguation problem or the unknown address problem. So to understand this example, to understand this problem, I have an example here, but before I would like to mention that loads and stores have two different types of latencies. There is address calculation, and there is also the latency of going to memory to load or to write. Now let's understand the problem here. As I said before we dispatch load or store instruction, we need to compute the address, right? So to compute the address of this store, it takes 100 cycles. It takes 100 cycles to compute the address of the store. And to compute the address of a subsequent load in the program order only takes 2 cycles. And the question is, okay, we have the address of this load. Can we dispatch this load? Right? Can we dispatch this load? Well, no. Why? Why we cannot? Because maybe this load is depends on that store. Maybe what this load is going to access in memory will be right by this store. Right? Well, but to check if there is a dependency between the loads and store, we need the address. But the address of the loads takes 2 cycles to complete, and the address of but the address or the computation of the address of the loads takes only 2 cycles to complete, while the computation of the address of the store takes 100 cycles. Right? This is the problem. A younger load can have its address ready before an older store address is known. So this is the memory disambiguation problem. And here we have another illustration that will help us understand that the problem is even bigger. So we have the first store that takes that the address takes 900 cycles to complete, and we have a subsequent store that the address takes 500 cycles to complete. And after that, we have a subsequent load that the address takes 2 cycles to complete. And it's important to mention that this load is going to access 4 bytes in memory. And that means that this load here is going to access 4 different locations in memory. And for that memory location, we need to check if there is no previous store that's going to write to that to these locations. For example, the first store here maybe is going to write to the last location of the 4 location that this load is going to access, and the second store maybe is going to access, maybe is going to write to the second location that this load is going to access. Right now, think in modern architecture. For example, we can address byte, 2 bytes, 4 bytes, and 8 bytes, and for all the location that a load is going to access, we need to check if there is not a previous store that's going to write to this location. So that's make the problem worse. It's not good. So a load dependency status is not known until our previous store addresses are available. And the question is, how does the out of order engine detect dependence of load instruction on our previous stores? The option number 1, we can wait until our previous stores are committed, and we don't need to check for address match. So for example, if we have 15 or 20 stores, right, we just wait, and we just computed the address of a load. We just wait until these 20 stores completed, right? They update the memory so that we can dispatch the load. But this is not good. Why? This is not good because maybe the load, right, do not depend on any of these stores. So that's why it's not good for performance. And the second option is to keep a list of pending stores in a store buffer and check whether a load address matches a previous store address. So this is a better approach. And going forward, we will see why and how this works. So another question is, how does the out of order engine treat the scheduling of a load instruction with regards to previous stores? And we have 3 approaches here. The first is the conservative approach. We can store the load until our previous stores have computed their address or even returned for the machine. This is also not good for performance. And the second approach is the aggressive approach. And here we assume that a load is independent of unknown address, and we schedule the loads right away. This is good, but for this we need to check, right? Because here what we are doing is predicting. We need to check if the prediction is right or not. And if the prediction is not right, we need to execute the load again. And there is another approach, that is the intelligent approach. Is also prediction and is similar to the aggressive approach, but the difference is that here we use a sophisticated predictor inside of the pipeline that we make prediction if a load is dependent on a previous store based on the behavior of the program. And here we also need to check if the prediction is right or wrong, and if it's wrong, we need to execute the load again. And here we have an illustration of the performance of these 3 approaches, and the perfect or intelligent approach is better in terms of performance, and predicting stores and loads dependencies is important for performance. So now let's understand data forwarding between stores and loads. We are going out of time. We go a little bit faster. We cannot update memory out of the program order. We need to buffer our stores and load instructions in instruction windows. And another point that is important is, even if we know all the address of past stores, when we generate the address of a load, 2 questions still remain. First, how do we check whether or not it is dependent on a store? And the second, how do we forward the data to the load if it's dependent on a store? So modern processor uses a load queue and a store queue for this, and can be combined or separated between loads and stores. A load searches the store queue after it computes its address. Why? Here we are assuming that when a store finishes the computation of its address, the store writes its address in a buffer that's called store queue, so that when a load finishes the computation of its address, the load searches this buffer to see if it's dependent on a previous stores. A store searches the load queue after it computes its address. Why? So here we are assuming that we are using prediction to dispatch loads, right? If we predict that a load is not dependent on previous store, we still need to check if it is true or not. And to be able to check, we need to use a buffer or a structure in which, before we dispatch the load write its address to that structure, so that when a previous store finishes the computation of its address, the store will search this buffer, that is also called load queue, to see if there is not a subsequent load that was already sent to memory that depends on a previous store. So now let's talk about out of all the completion of memory. It's going a little bit out of time because we are going really to understand how it affects the memory model in a couple of slides. Just hold on. So when a store instruction finishes execution, it writes its address and data in its reorder buffer, or it writes its address and data in its reorder buffer entry or the store queue entry. And when a later load instruction generates its address, it first search the store queue with its address and access the memory with its address. So why we need to access the store queue and the memory? Well, if the value is not at the store queue, well, we need to go to memory, right? Because the value may be at the store queue or maybe at the memory. So we need to receive the value from the youngest older instruction that wrote to that address, either from the reorder buffer or store queue or from memory. This is a complicated search logic implemented as a content addressable memory. And content here is the memory address, but we also need to take in consideration the size and the age. Going forward, it will be clear. And it's also called the store to load forwarding logic. So I think we don't have time to go through this, but here I would like to illustrate why renaming memory address is difficult. But when we are performing renaming of registers, we can use indirection because register state is small, right? We can have the entries inside of the register alias table can point to an entry in the reorder buffer. So we can use indirection. But we cannot do that with memory because we use 48-bit of memory address. And with that, we can directly address every byte of 256 terabytes of storage. And if we try to use indirection with when renaming memory address, well, we will need a register alias table. Oh, not register. We need a structure with 256 entries. And in total, it will be 256 terabytes because each entry will be 1 byte. And we cannot have it inside of a pipeline. So that's one of the reasons why renaming memory address is difficult, because we cannot use indirection. And I encourage you to watch my CUPCon talk to really understand this. So now let's understand why store to load forward is complex, right? Because we talked that, okay, a load, when have its address, need to search the store queue. Now we understand why this search is complex. Well, the search is complex because the content addressable search. We cannot use indirection because memory state is large. It's also a range search because for every, for example, for every memory location that a load is going to access, we need to check if there is not a previous store that's going to write in that location. It's also age-based search because we need to get the value that was writing to, because we need to get the youngest value that was writing to that address. And the load data can come from a combination of multiple places, right? One or more stores can be in the reorder buffer, and others, maybe we need to go to memory or cache. And if that is not a reorder buffer, we need to go to memory. So here I have an example illustrating the real the buffer, right? Here I'm only illustrating the content addressable search, but in real modern computer, we need to take in consideration also the range search and the AZ based search. But here I'm only taking consideration the content addressable search. So when a load finishes the computation of its address, we use the address of the load, right, to check every entry of the real buffer to see if there is a match. So we need to search out, right? We cannot use indirection, right? We cannot go directly to a special entry where we need to check if there is an address or not. We cannot do that here. We need to search, right? Because it's a content addressable search, right? We need to check every entry of the real buffer to see if there is a match. And if there is no match, we need to go to memory. And here we can spend a lot of time searching this buffer. And if there is no match, well, we need to go to memory again. And for example, when going to memory, we can miss a tele1, we can miss a tele2, we can miss a tele3, and we can miss a DRAM, and we need to go to disk. So you see why this search is complex. And here we're only talking about the content addressable. So now let's see how this real buffer affects the visibility of store operations, and also how it affects the total store memory model. So for that, let's see how this buffer works a little bit. So we have the first instruction, that is a store, and it takes 100 cycles to compute the address of the store. And when the store arrives, what we do, we allocate an entry for that store at the real buffer, and the store becomes the youngest entry in the real buffer. And we also have the address bit and the valid bit and the value in each entry. So for this case, for the store, this address takes 100 cycles, and because of that, the address and the value are not ready. So the valid bit is 0, and the address bit is also 0. And after that, the second stores arrive, and to compute the address of the store only takes 2 cycles. So, okay, the second store arrives, we allocate an entry for the second store, and the second store becomes the youngest instruction in the real buffer. And to compute the address of the store only takes 2 cycles, and the value of the store was already produced by another instruction, so that it's ready. So we have the address, we have the value, we can update the real buffer where we set the valid bit, the address bit 1, and the valid bit to 1, and the value that we need to write to that address is 25. So we can see it's 25. So now we have completed. We didn't wait for the first store to complete, right? Well, we still the first store still computing its address, but we already finished the execution of the store, of the second store, right? But what's important to mention here is that the store, the second store, we only update the arbitrary state. We only update the memory when the first store completes. When the first store completes. Why? Well, because the real buffer is a first in, first out structure. And this is how we provide precise exception. And this is how we don't need fences between stores and store in ECT6 architecture. Why? Well, even though we completed the execution of the second store cannot update the memory. The value is in the buffer. And if a local load tries to access the value that was produced by the second store, we can access that from the real buffer. But the second store cannot exit the real buffer until the first store completes, because the second store can only exit the real buffer when it becomes the oldest instruction in the real buffer.
Filipe, sorry for interrupting. Just to let you know that the ordinary time is over. So if you can please catch up, and then we have a couple of questions, but I think you can get them into the lounge.
Okay, so can we have 2 minutes?
Yes, 2 minutes, yeah, for sure.
Okay, so here we saw why we don't need store fences, right? Because we have the guarantees that a subsequent store will not update the memory until the first store completes, right? So the reload buffer inside of the microarchitecture of x86 give us this guarantee. So we don't need fences for that. We have the guarantee that a subsequent store, we only update the memory. The result will only be visible when the first store is complete. Sorry again. And another thing important to mention that is because we have the buffer, it affects the visibility of other cores. Because the value of this address, for example, when the third instruction that's allowed is going to access, right, this value, the value that we're writing by the previous store, that's the second instruction, it will find the value at the rear of the buffer. But if another instruction in another core try to access the same address, right, try to load a value from this address, well, the problem is if we need to go to memory and it will load a different value. And here I have a bug. Here the load should be register number 2 to be equal with the second instruction. Sorry for that. So this is how two threads can have different point of views of on how memory operations took place. Because one have direct access for the real buffer, but another one has no access to the real buffer and need to go to memory. And this value is at the real buffer, and we only exit until the stores becomes the oldest instruction in the real buffer. So I think I will complete. I have more here, but how, for example, how the total store, how the real buffer interacts with hyper-threading, for example, but I don't think we don't have time to go through this. So thank you very much for attending my talk, and see you next time. And that's all.
Thanks a lot for your session, Filipe. I think we can
important context over here, but that's all. Thank you very much.
Thanks a lot.